Good morning. I am now going to show you how to do a calculated chi-squared equation by hand. I like to define the two different types of chi-squared equations as one-dimensional and two-dimensional based on how many variables there are. We did the first question on this practice sheet as a one-dimensional chi-squared equation, and go see my other video to find that. We're now going to do the second question as a two-dimensional chi-squared equation because there are two different variables. Now I'm going to read the question. 17 of 45 beluga whales that died downstream from a factory contained evidence of an industrial toxin. 5 of 29 beluga whales found dead upstream from that same factory contained a similar toxin. Is the likelihood of finding the toxin significantly different when comparing upstream and downstream whales? So first we need to write a null hypothesis. So our null hypothesis. There is no difference. No difference. That's what makes it a null hypothesis. There is no difference. What is there no difference in? There is no difference in the likelihood, that's not an easy word to spell, of finding the industrial toxin in dead beluga whales upstream or downstream of a factory. Now, in real life, you would have some more specifics about what toxin it was and what factory it is, but this is what we have right now. So we have multiple variables here. We've got we've got our dead whales, we've got them with or without toxin, and we have them upstream and downstream. So we're going to make a chart. So I'm going to start here with toxin present and toxin absent, and then totals. And then I'm going to have upstream and downstream, and again, totals. Trying to make half-decent lines here without a ruler. Oh, and then I'm going to make my observed and expected dotted lines. I'm not giving myself very much room for observed because I just have to write a number, but for expected I want room to do a little bit of math. So observed and expected, observed and expected. So two variables, two-dimensional. So what are observed? 17 of 45 beluga whales that died downstream contain evidence of the toxin. So that means 17 beluga whales downstream had the toxin. So toxin present downstream, we had 17 beluga whales. 17 of 45. That means there were 45 whales total downstream. 45 minus 17, that means there must have been 28 whales that didn't have the toxin. 5 of 29 beluga whales found dead upstream. So upstream, we had 5 with the toxin, and there were 29 total, which means of the 29, 24 must have been no toxin. So then our totals over here, 24 plus 28, and 5 plus 17, which gives us a grand total of 74. And I like to double check. 22 plus 52, 74. 29 plus 45, also 74. Now, when we did our one-dimensional, our expected was our total divided by the number of categories. But now we have two-dimensional. So now we have the number of categories this way and the number of categories this way. So we have these totals and this grand total. So now our expected value is the row total times the column total divided by the grand total. And that is going to be different for each and single one of these examples. So for here, where the toxin is present upstream, the row total is 22, and the column total is 29, and the grand total is 74, which gives us a upstream expected value here of 8.6. So I'm going to do that for each one of these. So here, for this number needs a pair. So for this observed 17, the expected value is going to be the row total of 22 times the column total of 45 divided by the grand total of 74, which is 13.4. For this one, this observed, we need an expected value. Here the row total is 52. The column total is 29. Our grand total is still 74, and that gives us 20.4. For this one, our row total is 52. Our column total is 45. Our grand total is still 74, and that is 31.6. And I like to double check. So 8.6 plus 20.4 is 29. Yay! 13.4 plus 31.6 is 45. Yay! 13.4 plus 8.6 is 22. Excellent. Any little check marks. 31.6 plus 20.4 happens to be 52. Excellent. So this is a way to double check your math, because they're sharing, the observed and the expected are sharing these total columns, so they should add up. So now that we have those numbers, we need to put this into our equation again. So chi squared equals the sum of observed minus expected squared over expected. Now we're going to add this part of the equation over as many times as we have observed and expected values. So chi squared equals observed minus expected squared over expected plus, because that's what that sum of means, plus observed minus expected squared over expected, that's a little sad, plus observed minus expected squared over expected. So we've got one pair of observed and expected, two pairs, three pairs, four pairs. So we're going to add this 4 times. Five minus 8.6 squared over 8.6. 24 minus 20.4 squared over 20.4. 17 minus 13.4 squared over 13.4. And 28 minus 31.6 squared over 31.6. Chi squared equals and then I like to go down the column. Look at this. Negative 3.6, 3.6. Remember how I said how sometimes the numerators match? We have one negative and one positive canceling each other out. That happens a lot. That happens so much that when it doesn't happen, I question it. I go back and double check. Whoa, 3.6 again. So I bet you anything 28 minus 31.6 equals negative 3.6 to match negative, positive, positive, negative. Just like before, 2 negatives, 2 positives. So I'm going to add those up. And we get 3.5. So remember, again, this is our calculated chi-squared. We still need to figure out what our critical chi-squared is. So that requires our table of critical values. So before, we were looking at one-dimensional equations where the degrees of freedom is the number of categories minus 1. But now we're in a two-dimensional. So just like with a line, you just measure it, but with a square, you measure the length times the width. Two-dimensional, we're going to measure our rows times our column. So we're going to do the number of categories in rows minus 1 times the number of categories in columns minus 1. So we're going to go back to up here. We have 1, 2 categories in rows and 1, 2 categories in columns. So our degrees of freedom is our number of rows minus 1 times our number of columns minus 1. So we have 2 categories in rows, and we have 2 categories in columns. So it's like 1 times 1 equals 1. Pretty easy. Which means up here, we're on the first row. And remember, this is 0.05. This is our alpha. This is the acceptable amount of error. So this is the amount of error that scientists have agreed upon across the board. So this is our critical value. And this time it's 3.841. Anything, if our calculated value is greater than this, we reject it. It's beyond what is acceptable by the most of the scientists. 0.05 is our cutoff line. If our calculated is less than, we accept it. Greater than, we reject. So we're going to put that number, 3.841, into... So 3.8 is bigger than 3.5. So calculated chi-squared is less than critical chi-squared. Therefore, we accept our null hypothesis. Now it's not less than by a lot, but it still is less than, which means we accept our null hypothesis. So what would we write for a null hypothesis? We write the exact same thing over again as our concluding statement. There is no difference in the likelihood of finding industrial toxin in dead beluga whales upstream or downstream. of a factory. So now that does not mean that the factory is not putting a deadly toxin that's killing whales. It just means that the likelihood that the whales would have toxin in them upstream or downstream is the same. There is no difference. So that's how you do a two-dimensional equation. There are 2 more questions on our sheet. I recommend that you practice them for yourself. You can do the salmon one as a one-dimensional, your 2 variables being salmon or non-salmon. And you can do Joe and Fred looking for leaky pipes as a 2-dimensional, where your 2 variables are Joe and Fred and leaky and not leaky. Good luck!